Hello, everyone. It's me, Mr. Chardy. I'm here recording Chapter 10, which is our unit on motion and momentum. Section 2, which is about acceleration, from our book for our reading today, because I am not here. So, I'd like you to pay attention very carefully as I go through my lecture and be prepared for the work that has to come afterwards, okay? Today, you're going to have two papers. So, when you watch the first few seconds of liftoff, a rocket seems to barely move. With each passing second, you can see it moving faster and faster until it reaches its enormous speed. How could you describe the change in the rocket's motion? When an object changes its motion, it's accelerating. Acceleration is the change in velocity divided by the time it takes for the change to occur. So if I write that out, acceleration is equal to velocity divided by time. Okay, this comes off from what we talked about previously in my other lecture. A equals V over T. Now, this often is referred to in the change in speed. But as you will see later, the acceleration can also come in from a change in direction. Okay? So the car could be going the same speed, but it could be going around a corner. And because it's changing direction, it is accelerating. All right? Like velocity, acceleration has a direction. If an object speeds up, the acceleration is in the direction that the object's moving. If an object slows down, the acceleration is the opposite. What if the direction of the acceleration is at an angle? Then the direction of the motion will turn towards the direction of the acceleration. Essentially, what it's saying is that if you're speeding up, you're going in the same direction. If you're slowing down, then you're going in the opposite direction. Okay? Speeding up. You first get on a bicycle and begin to pedal. The bike moves slowly as first, but it speeds up as you keep on pedaling. Recall that the velocity of an object is the speed of an object, and its direction of motion. Acceleration occurs whenever the velocity of the object changes. Because the bike's speed is increasing, the velocity of the bike is changing. As a result, the bike is accelerating. Look at this toy car right here. It's accelerating because it's speeding up. The speed of the car is 10 centimeters a second after 1 second. It's 20 meters a second after 2 seconds, and it's 30 meters a second after 3 seconds. Here, the direction of the car's acceleration is the same. It's going towards the right. But you can see you start at 0, then you go to 10, then to 20, then 30, and keeps on going faster and faster each second. Okay? That's what acceleration's about. It's not how much distance you travel, it's how much speed. So how much distance you can travel in a time. Slowing down is the opposite. Now let's suppose you're riding your bike at the speed of 4 meters a second and you applied brakes. So you have those little hand brakes. This causes you to slow down. When you slow down, your velocity changes because your speed decreases. This means that acceleration occurs when an object slows down, as well as when it speeds up. The car in Figure 8 is slowing down. During each of its time intervals, the car travels a smaller and smaller distance, so its speed is decreasing. See, in the first second, it went 30 centimeters. In the second one, it went only 2 spaces, so 20 centimeters. And in the third second, it only went 10 centimeters. In both of these examples, the speed's changing, so the acceleration is occurring. Because speed is decreasing in the second example, the direction of acceleration is opposite to the direction of motion. Anytime an object slows down, its acceleration is opposite to the direction of its motion. So you have an object going forward and it speeds up, so it's in the same direction. Positive acceleration. You got an object going forward and it starts to slow down. They are in opposite direction. They're ops. And so, oh, you can't really see that. Since they're ops, here, I'll draw it right here. This is called negative acceleration. And this guy is positive acceleration. Big old plus sign. The velocity of an object also changes if the direction of the motion changes. Then the object doesn't move in a straight line, but instead it moves in a curved path. The object's accelerating because of the velocity is changing. In the case of the direction of acceleration is at an angle to the direction of the motion. Again, imagine yourself riding a bike. When you turn the handlebars, the bike turns. Wow. Because the direction of the bike's motion has changed, then the bike has accelerated. The acceleration of the direction of the bicycle has turned. It's staying the same speed, but its direction is changing. So it has to be accelerating. Figure 9 shows another form of acceleration. The ball starts moving upward, but the direction of the motion changes its path and starts to go downward. All right, you guys see that? You throw it up, and then it starts to go down. Here, the acceleration is downward. The longer the ball accelerates, the more the path will turn towards the direction of acceleration. And what causes this ball to go downward? Gravity. As we'll find out a little bit later in this unit, there's this force called gravity, which pulls stuff in towards the earth. So, as you throw something up, its force is going to decrease and eventually gets too weak to where gravity starts to have more effect and pull it down. Calculating acceleration. If an object is moving in one direction, we can easily calculate its acceleration. All we need to do is take the final speed. Let me get a new page going. We need to take the final speed. We need to subtract the initial or starting speed. And we need to divide by the time it takes. Now, this takes a while to write out, so we, as mathematicians and scientists, use an abbreviation. We say S for speed, and then a little subscript F, so final speed, minus initial speed, so SI, over T. Some people will use S2 minus S1, so the second speed minus your first speed, over T, okay? It doesn't really matter which way you go about it. It's good to see that there are these options. What's important to note is that you take this equation, acceleration, acceleration, and acceleration. In this equation, the time is the length of time to which the motion changes. And the SI units, acceleration has a unit of meters per second squared. Meters per second per second. But here's a little problem we'll try out. We have a bus whose speed changes from 6 meters to 12 meters over 3 seconds. So we go from 6 meters a second to 12 meters a second over 3 seconds. Okay? So let's calculate it out. I'm gonna get a different color because I want to. Let's get purple. Purple's a nice color. So, what's our starting speed? Y It's 6 meters per second, of course. So I'm going to put SI. What's our final speed? Well, that would have to be the speed at the end. That would be 12 meters per second. I'm going to put SF. And what's our time? Well, it's over a period of 3 seconds. So I'm going to put that as my T. Now I can put this into my equation. A is equal to SF minus SI over T. So SF I said was 12 minus SI I said was 6 over T, which is 3. Now, could you tell me what 12 minus 6 is? Good, it's 6 divided by 3. Who could tell me what 3 or 6 divided by 3 is? Cool, it's 2. So that's 2 meters per second, but that's a weird way to write it. I don't like that. So we're going to write 2 meters per second squared. Okay? And we check in our answer, and we see the work's the exact same as we got. And it's 2 meters per second squared. Wow. Let's try out some of these problems as well. So a train increases its speed from 7 meters a second to 17 meters a second in 120 seconds. So let's write that down. I'm going to use blue for this one. So we have from 7 meters a second to 17 meters a second over 120 seconds. Wowie zowie. Okay? So here is what I need you guys to do. First, start by identifying your starting speed, your initial speed. That's going to be 7. What's our final speed? 17. And what is our time? 120 seconds. So I take that and I put that into the equation. My final speed, which I said was 17, minus my starting speed, which was 7, over 120. So now, could you tell me what is going to be 17 minus 7? If you guys need calculators for any of this, you guys know where they are. Please return them, okay? This is needed for other classes, so do return my calculators, please. 17 minus 7 will give me a 10 over 120. Now, I don't know what 10 over 120 is mentally, so I'm going to use a calculator. There's no shame in using a calculator, but we got to make sure we input it right, and we acknowledge when we need to use a calculator. It's faster to not use it, but it's more important to be correct and use it when we have to. So I put this into my calculator, and I find out it's 0.083 repeating. And so I'm just going to go to 3 decimal places. I'm going to say it's 0.083 meters per second squared. That's my acceleration. All right, can we dig it? Let me go with this nice pink. A bicycle accelerates from rest to 6 meters a second in 2 seconds. What's the bike's acceleration? So we go from rest to, what was it? 6 meters a second? Yeah, 6 meters a second. In 2 seconds. Kind of wrote that pretty close together. In 2 seconds. There we go. So here's the tricky one. We could say that we started at rest, because that's what they kind of tells us. It goes from rest to 6 meters a second. So this is our SI. And this is our SF. But then the question then becomes, what is rest? Well, let's think. If you are not moving and you're resting and you're standing still in one place, what's going to be your speed? It's going to be 0 meters a second. So Now that we have a number we could put in, we're going to do 6 minus 0 over 2. 6 minus 0 is 6 divided by 2. And we should be able to say what's half of 6. It's 3 meters per second squared. Don't forget your units at the end. I would love to see your units, okay? Let's see how much we have left. Oh, only 2 pages. Nice. So positive and negative acceleration. An object's accelerating when it speeds up, and the acceleration's in the same direction as the motion. An object's also accelerating when it slows down, but the acceleration is in the direction opposite. How else is acceleration different when an object's speeding up and slowing down? Suppose you're riding your bike in a straight line, and you increase your speed from 4 to 6 in 5 seconds. We can calculate it. 6 minus 4, which is 2 over 5, 0.4. When you speed up, your final speed is always going to be more than your starting speed. So subtracting will always give us a positive number. Bigger number minus smaller number will always be positive. So, since that's the case, acceleration must be positive when we speed up. Now let's suppose that we slow down. We go from 4 to 2 in 5 seconds. So we do our subtraction. 2 minus 4 is negative 2. Negative 2 divided by 5 is negative 0.4. So since our final speed is less than our starting speed, we're slowing down, and our acceleration is always going to be negative. Small number minus big number, always negative number. Does that make sense, guys? Big minus small, positive. Small minus big, negative. And that's why order matters. Our final speed's going to be less than our initial speed. Our acceleration will be negative. Like with speed, we can graph acceleration. Now, if you remember, graph paper, wow. If you remember, on our graph for our speed graph, we had distance and we had time. And stuff can be going up and going down and staying horizontal, yada, yada, yada. Our acceleration graph is very similar. On the horizontal, or the left-right, we have time. And on the vertical, or the up-down, we don't have distance, but we have speed. And here, we would put the title of the graph. So this is an acceleration graph. Okay? And yes, this can also go up and down and up and horizontal and down and up and down, horizontal and back up. Okay? So the motion of an object that is moving is a single direction can be shown in a graph. So that means going forward. This type of graph, speed is plotted on the vertical, the up-down, and time is on the horizontal, the left-right. Take a look at this figure. On section A of the graph, the speed increases from 0 to 10 over the course of the first 2 seconds. So what we do is 10 minus 0, which is 10, divided by the 2, and that is 5. So the acceleration is 5 meters a second. The line in section A slopes up to the right. So this is called positive. If in math you started graphing it, you have to go up, you're going positive. Up as you go to the right, you're positive. An object that is the speeding up will have the slope going upward. Now we take a look at section C right here. We go from 4 seconds to 6 seconds. So over the course of 2 seconds, so 2 seconds have passed. We go from 10 meters a second to 4 meters a second. So what we're going to do is we're going to do 10 minus 4, which gives us a 6. And then we're going to divide by 2, and that gives me 3. But wait, Wait. 10 minus 4 over 6 gives me a 3. That's right, but I know I'm going down. And going down, I should have a negative because I'm slowing down, right? Oh, you know what I did wrong? I put this order in the wrong way. So I'm just going to take an eraser. I'm going to fix it. I'm going to rewrite my work. We have erasers on our pencils for a reason. So 4 minus 10 over 2. Oh, this was supposed to be 2. Whoopsie-doo. Okay. So this will give me negative 6 over 2, which will give me negative 3 meters per second squared. So now this makes sense. Okay. If going up is positive, then going down has to be negative. So make sure you check your work and it makes sense with your answer. You go through and do these. On section B, which is this horizontal line right here, the slope is 0. It's horizontal. The change in speed is 0. So it's still moving, but it's not speeding up and it's not slowing down. It's staying at 10 meters a second. It's not stopped. It just keeps going at the same speed. There's no acceleration. Do some practice problems before you guys get your work. So we want to compare and contrast speed, velocity, acceleration. Pause the video if you think you can answer it. Okay, so speed is distance over time. Velocity is speed with a direction, so distance, time, and a direction. And acceleration is a change in velocity, so either a change in direction or a change in speed over time. All right, does that make sense? Okay, we want to calculate the runner who goes from 0 to 3 in 12 seconds. So I want you to stop. And now if you're ready to answer, let's see what happens. We go from 0 to 3 in 12 seconds. So if you remember our formula, it's the final one, our SF, minus our starting one, SI. So 3 minus 0 over our time, 12. 3 minus 0 is going to give us a 3 over 12. And once I put this into my calculator, I get 0.25 meters per second squared. Okay? And the last question we're going to talk about is an object falls with an acceleration of 9.8 meters per second squared. So that's this fancy little thing we call gravity. Okay? Gravity pulls stuff down at 9.8 meters per second squared. So after 2 seconds, how fast is the object going to be moving? Stop here for a second. Okay, so we know at 0 seconds, the object is moving at 0 meters per second. Wow. At 1 second, the object is moving at 9.8 meters per second. And after 2 seconds, it's moving at 9.8 plus 9.8. So that will be 19.6 meters per second. Okay? So after this, you should have some time in order to work on your papers. Please work. Please feel free to ask questions with your sub. And I will expect these ready and done when we come back, okay? You guys have a great day. Bye-bye.